Hey everyone, we're going to take a look at simplifying radicals in this video. So first off, we got to figure out what a radical is and what the parts of it might be. A radical is just this square root symbol, but sometimes it's not a square root. You'll find what root you're looking at by the index. In this case, the index is 3. In this case, the index is 4. In this case, when there's nothing there, your index is 2, and that's a square root. That's the one you see the most, probably up until this point. Underneath the radical is what we call the radicand. And what we're going to work on is simplifying radicals, basically the radicand based on the index of the radical. So we have to start by generating our list of perfect squares, cubes, and fourth roots. I recommend pausing the video now to write down all these numbers. When you create these lists, you're basically taking numbers and squaring them. So we have 1 squared, 2 squared, 3 squared, 4 squared, and so on and so forth. 5, 6, 7, all the way up to 15 squared. And for the cubes, 1 cubed, 2 cubed, all the way up to 7 cubed. Cubed just a third power, like cube root would be a 3 as an index. And then fourth roots, 1 to the 4th, 2 to the 4th, all the way up to 5 to the 4th. Obviously there are more perfect cubes, squares, fourth roots out there, but for the sake of our class, I don't think we need any numbers other than these. So remember, for squares, it's whatever the number is to the second power, to the third power for cubes, and fourth power for fourth roots. So let's talk about how we're going to use these perfect squares, cubes, and fourth roots. If we have this number, and if we had, say, square root of 36, that's a perfect square. That gives us 6, right? Because 6 times 6 is 36. So the opposite operation, which is square root, gives us a 6. Square root and square cancel out. They're inverse operations like addition, subtraction, multiplication, division. 6 squared is 36, and you can see they cancel out and provide you with a 6. But what if we don't have a perfect square? 72 is not, because if you look at your list, you go 36, 49, 64, you skip 72. It's not a perfect square. So what we look to do is take out the biggest perfect square. So what we do is we try and find what perfect squares are divisible into 72. I can find a few of them, but we look for the biggest one, and that's 36. And it goes in twice. So I put my radicals as a perfect square, and then you basically have your leftover not perfect part. We said the square root of 36 is 6, because 6 squared creates it, and you just leave the not perfect part, and that's how you simplify it. Now say you picked a different perfect square, one that's not the biggest one. Say I picked, 9, because 9 goes into 72 8 times. Square root of 9 is 3, because 3 times 3 creates 9. But that's not fully simplified, because if you look at 8, and then you look at your perfect square list, 4 goes into 8. So we'd have to simplify it again. So this is why you want to pick the biggest one, because you're going to have to do a lot of steps if you don't pick the biggest perfect square. And look, you end up with the same answer. So the goal is really to take the biggest perfect square out of each radical if you start with a not perfect square. Let's look at another one. This one has a coefficient on the outside. So let's look for the biggest perfect square. It goes into 20. I know that it's 4 because you can only look at numbers that are less than or equal to this number in the radical, because nothing else can be divisible into it. 16 doesn't go evenly into 20, nor does 9. 4 is the only one that goes in evenly into 20, so we use 4 and whatever multiplies by 4 to get to 20, which is 5. right? 4 times 5 is 20, so that's how I'm allowed to break it up. Perfect square, and then the leftover not perfect. Square root of 4 is 2. Not too bad, right? How about this one? Can you think of two numbers, well, the same number, that multiplies by itself to provide a negative number? Like in this case, 2 times 2 gave us 4. And that's how we took the square root of 4 and got 2. There are no numbers that if you multiply them by themselves will give you a negative number, at least no real numbers. So your answer here would be no real solution. And that's when you have an even index. This is really important because you could have an odd index and a negative and it would work. Even index and a negative radicand. Thinking back to those vocab words we started with, even index in this case is 2, and the radicand is a negative 16. So that's a no real solution. And that's all you'd answer. Let's look at a cube root. Go back to our list of perfect cubes. Oh, 27. The one I'm given here is a perfect cube. So I said that 3 cubed gave me 27. So the cube root of 27 must be 3, because what that's saying is 3 times 3 times 3 is 27. Right? It's the inverse of this. So that's easy. You do the exact same thing if it weren't a perfect cube as you did, say, on this problem. Find the biggest perfect cube and leave what's not perfect. And just simplify the problem from there. What about this one? So this one I have an odd index and a negative under the radical. I can simplify this because if I multiply a negative number 3 times, the same negative number, I get a negative number, right? It's only when it's even, so if I had done one more time, then I'd have to have a positive. So in this case, I could simplify. And the biggest perfect cube that goes into negative 250 is actually negative 125. So, going all the way back to our page where we generated the perfect squares and cubes, these could also be negative. But these, with the even index, squares and fourth roots, could not be. So now, negative 125 times 2 will get us negative 250. The cube root of negative 125 is negative 5. And there's your answer. Just multiply numbers that are on the outside. And that's it.